Question 3. So we're now given a function f and g, which go from Rn to Rm, and these functions are differentiable. We then define a function h, which is the dot product of f and g. And because it's the dot product, h goes from Rn to R. Part 1 is to show that h itself is a differentiable function, and part 2 asks us to show that the gradient of h can be expressed like this. And the t that we're seeing there, that's just a transpose. And throughout this question, I'll be very careful to distinguish between vectors and scalars. So the first part is to show that h itself is differentiable. So immediately, f, g are differentiable. And it goes from Rn to Rm if and only if each of the component functions are differentiable. And the component functions go from Rn to R. Instead of saying each of the component functions, I'm going to say all of the component functions, just to give it a little more emphasis. So then we recall h. Oh yes, and I should put arrows on top of f and g because they are vector valued. There's no arrow on top of h because h is scalar valued. We defined it as follows. H was this. And if we simplify it, that's just first component function. And component functions are scalar valued, not vector valued. And there should be n of them. And we simplify. And I'm going to index it by using j. So j goes from 1 to m. So the product of differentiable functions is differentiable, and the sum of differentiable functions is differentiable. So therefore, h is differentiable. Because it's the sum and product of other differentiable functions. Too far down. Next up, we will recall x is an Rn. And now we want to take the partial with respect to xi. With respects to xi. And we would need to use product rule. Oh, and I mean the partial of h, by the way. So di h, di xi. So that's sum and derivative of the first times the second plus the first times the derivative of the second. Just like that. And then we recall the Hessian matrix. Sorry, not the Hessian matrix. Not the Hessian matrix, sorry. This is the total derivative. And the total derivative looks like this, as you can see. And this total derivative can be represented as a n by n matrix. So this thing that you're seeing there, that's just the jth row ith column. So ijth entry of this guy. And quite obviously, we could do the same thing for the g function as well. So if I write an equal sign, so if I go dot, 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 and then now I continue down here, that's just the sum of this. And it's f with a hat because it's vector valued. Oh wait, no, I should write it like this. I should write it like this. And we just do a quick check. This is a real value because the entries of the total derivative here are real values. And the same thing can be said, you're real valued because component functions are real valued functions. And the same logic applies with this and with that. So everything we're working with here are ultimately just, it's just an expression of product of real values and sum of real values. So if I took that matrix and I transposed it, then I'm interchanging the entries because the rows become columns and columns become rows. And then we continue. So again, this is just a real value, and this is just a real value. And this is a real value coming as an entry of the matrix. So really what we're looking at here is we're looking at a multiplication of a n by n matrix by n by 1 column matrix. So let me write that down. So this dot there, that dot's just regular multiplication of numbers. On this next line, however, this dot here, and I'll make it red, just to really signify it. That red dot there is matrix vector multiplication. And just as an aside, this here you could switch up the order because these are still real valued. And again, this will be like this. And this red dot here signifies matrix vector multiplication. And actually what we have is that we have the ith entry overall. So the red dot, so I'll change it to the blue dot so it doesn't, so we don't confuse it with the other red we're seeing here. The blue dot is to represent matrix vector multiplication. Because this was n by n, but we're taking the transpose, so it's n by n. N by n, you're going to be n by 1, and you're the same story. So what we would expect, or not we expect, but we have something that's n by 1. And then I'm going to color coordinate this one too. I'm put a green eye here, green. We take the ith component of the column vector. And the values for I range from 1, I believe, to n. That should be right, yeah. So overall, what do we have? The partial that you see here, that partial is equal to this entire expression down there. So overall, wasn't there another index? No, it's just dih dxi. That's going to equal to this. And again, I'll use the blue dot. And for here, I'll use a green eye. So we're done. So therefore, what we have is the gradient of h is just this. Oh yes, and this is the gradient of h at vector x. Same thing up here. And we are done. Question 3.